Yeah, we're good.
I haven't been mic'd up.
You haven't been mic'd. Here I am looking at you.
Well, I was just, your reviews made me think.
We'll record the miking also.
Yeah, that's why that's really for the recording. Okay. You want to, let's turn you on. Testing. Test. 1 second. Probably want to put it in the middle. And, okay.
We're going.
Okay, thanks.
Okay, we have reached the last talk in this particular track, and I think we may have saved the best for last. So we actually do have a 5 o'clock slot in red and in blue 1, but this will be the last talk in this particular track. Okay, so thanks all for sticking it out this afternoon. Our final speaker, I'll just get out of the way and introduce Wes Widner.
All right, thanks, Bill. Hello, everybody. This talk was actually written for me several months ago. So, just a little bit of background, because Phil asked for some background, and I guess I do need to provide a little bit of explanation as to how this talk came about, how I'm here, and all that. I'm actually from the Augusta area. We moved up to Atlanta, and I joined the Global Threat Intelligence team for McAfee up there. That's where my security industry experience really started. That was the infancy of joining big data analytics to threat intelligence. So fast forward, not fast forward, but about 5 years after that, I joined Norse to create their malware pipeline. The initial requirements of the malware pipeline were really fuzzy. Just get a whole bunch of malware and do something with it. Just, I mean, that really was it.
Get some things together, do some stuff.
Yeah, just have to do some stuff. So that really was pretty frustrating. So several months later, we actually have, I wrote the proof of concept. We're on version 3 of the pipeline now. We have a pretty good idea of what a pipeline is supposed to do. So I wish it was this nice and polished when we started with it, but I came up with 2 major goals for the pipeline. The first one is automated malware analysis. Automated as opposed to manual. So we have a team of analysts in the office. They go to incident response and they pull apart a piece of malware and they write up all kinds of incident reports. My job is to provide them as much automated intelligence as I can. So looking over their shoulders, seeing what they do every time they open up IPro or something like that, and writing an automated way to generate that intelligence using usually Python. So that's the first goal, automated analysis. The second goal is taking all the automated analysis that we have through all the samples that we run through and come up with some machine intelligence. Now, if we get into specifically what machine intelligence is, because it's used a lot of times today, it's just a coverall, just a machine intelligence, when really it's just a SQL query. So we'll get into that. The malware pipeline can be divided up into 3 broad categories. There's the sources, the features that we pull out of those sources, and then the machine intelligence, or the intelligence that we generate from the features from the sources. So each one of these areas has its own peculiarities and its own guidelines. So for the sources, when we first started looking at the malware pipeline, we have some internal sources at Norse. Just to give you some background on Norse, what we do. The bread and butter of the company is passive sensors. You've probably seen the threat map on Norse's website. Very used in a lot of news things. But that's from passive sensors, honeypots. This pipeline or this project, is taking the data that comes from those passive sensors, or initially it was taking the data that comes from the passive sensors, the URLs that are straight, trying to find malware off of those URLs. And instead of being a torrent like I hoped it would be, initially it was pretty empty. So we had to go hunting for malware sources, samples. So there's two major types of sources. One is organic, and that's where you have live, malicious URLs that you're trying to pull data off of. What we found out is we'll ingest something like 500,000 URLs. Out of that, only 20% or so will result in a binary. Malware fights being analyzed at every step of the way. The first step is the server that you pull it off of. The server it doesn't want to give you the binary unless it knows that you're going to be infected. So there's all kinds of work with our crawlers that we have to effectively come up with a honey crawler. There's a Python utility that looks really promising. It's not the one we use, but it's called it's Thug. It's written in Python. Pretty much all of our tools are going to be written in Python, just because that's where we found most of the frameworks to be the best. So you have to present the right user agent. We actually spray our URLs with random user agents, and then that actually provides good intelligence later to see which user agents are accepted more by malicious sources. It gives us an idea, and we haven't started publishing this information, but we should, of which user agents are more targeted by malicious servers. So I can go ahead and tell you the result of that. Preliminary result is IE7 on XP, or IE7 on Windows 7. Yeah. So not the very latest, not really old, somewhere right there. What I found is most malware targets 2 versions of Windows back. So anyway, organic URL sources, they fight you, they send you every wrong error message. They will send you, well, they don't want to send the file, so they'll send trash data. They'll send they'll redirect you indefinitely. They'll keep reports open. So first thing we had to do for the malware pipeline is basically take into account failure every time we're going to scrape from an organic source. Second thing that we learned with organic sources is, when we go to different vendors to ask them for a sample of their organic sources, we have to be able to vet them for how good they are, how good the sources are. So what we found out is that volume and how many valid binaries are downloaded, the division of those two gives us a yield. A good yield would be about 20%. Average is around 15%. So the reason for that is most of these URLs that get published, they get taken down very quick because automated systems. The site operator, whatever. So organic sources, you can get a ton of URLs coming in, but you still only get relatively a trickle of binaries. So the second type of source is an artificial source, synthetic source. These are vendors that have a stream of malware that comes from someplace else. And what we found out later is that those other places are usually memory dumps or samples that are submitted from a website or something like that. So these are a lot safer because they're given to you in a stream, but they're also unreliable in the fact that if I'm given a memory dump, then that memory dump is usually has an invalid checksum in the header. So that means that the sample won't just run on a VM, which we'll get to in a little bit. So we have to gauge that source by how many valid runnable binaries it gives us. The good thing about a synthetic source is that it's a really high yield. So, and there's several places that you can get the synthetic binary. Synthetic sources from lots of stuff to play with, even historical things. So once we get a torrent of you know, a whole bunch of binaries coming in, well, we need to deduplicate them regardless of which source they come from. Another thing that we found out is that there's a lot of overlap in the different vendors. So what we do in our pipeline is we prioritize the free sources, look at Mozilla, their safe browsing stuff. It's a great source for free feeds. There's many others like that. And then we layer on the other sources after that and kind of come up with a delta difference between the different sources. What we found out is that at a certain point, the vendors just overlap entirely, and then it's just a matter of price, which one's got a better price. So after we got the malware in, or I should back up and say we're indiscriminate in how we pull sources down from these URLs. So we pull down HTML, JavaScript, images, whatever the server gives us. So we don't know that it's malware unless the feed, the synthetic feed, tells us. We'll get to that in a second. So the next thing we have to do is features. Pull out features from whatever it is we download. The features are the mining part of data mining. That's where you find, this is where all the work goes in. I don't know if any of you have ever worked with a machine learning system, but this is where the hard part is. The actual implementation of the algorithms is relatively easy. But pulling out the features is the hard part. So there's three main sets of features that we pull out of our binaries. The first is a simple surface scan. I say surface scan because this ideally should be one pass through the data. I've run into, every now and then I want to add more into this initial scan, like REST queries and going up to virus total and doing a hash query there and all this other stuff. That always bogs down the pipeline. First step, figuring out the MIME type, file size, just basic information about the file. This is not really making any calculations. This is really another initial step here is pulling out the strings in the file. Now, many of you have worked with pulling apart malware know that most malware is packed, so you're probably not going to get that much useful stuff out of a valid sample, but you will get some sense of where it came from. The second feature that we pull out, now we're getting into the real heavy lifting of actually statically analyzing malware. Based on what MIME type you pull out, you'll want to send it to a specific static analysis. For example, we have a separate string for PDF analysis, a separate string for Android analysis, a separate string for PE analysis. So I'll talk mostly about the PE analysis. The portable executables, DLLs, EXEs, COMs, those are for Windows files. That's generally where all the action is. So the static analysis of a PE file, first we unpack the file. We call out the several REST services with a hash the file, see if they've seen it before. If they have, there's really no reason to keep on doing more static analysis or dynamic analysis. So we're kind of short-circuiting the process. We want to see what DLLs that the file has, that the file reaches out to. We want to fingerprint the file. There's a really great framework for this. It's called PE Frame. It's Python utility, really great. It's actually freeware. Most of the stuff we use is freeware because this is, well, up until recently this was the Department of One because it was a proof of concept. So go through the file, everything short of running the file. So some of the more interesting things that are specifically part of machine learning, going through the file and generating an abstract syntax tree of the execution flow in the file. More advanced stuff based on the abstract syntax tree is to, most malware has short circuits in it where if it detects certain things about the system, it'll just shut off. Time, not able to reach certain servers, or if it detects a VM in the background, especially if it detects a debugger, it'll short circuit. Generating an abstract syntax tree in the static analysis phase lets you come up with tools to basically patch the malware to run all the way through completion. The ultimate goal here is to find C2 servers, command and control servers. So the other feature from static analysis that's really interesting is opcodes. There's a wealth of information with opcodes. So the opcodes from a assembly language perspective, each one of those instructions, an opcode, but not just one, combining it into, in analysis, it's called n-gram, or in natural language processing, n-grams for words. You use the same basic principle for malware or executables. The ideal size that we found is 5 gram or 5 opcodes at a time, and then using those as fingerprints through the rest of our analysis. Actually, pretty effective. So the last bit of features that we generate are dynamic. We actually have a cuckoo system. Has anybody here ever heard of cuckoo? Yeah. Cuckoo's wonderful for dynamic analysis and malware. Problem is it's not really built for scale. So we had to write some code around it to move the files where they need to be. And the biggest thing is keeping cuckoo from falling over and dying. So dynamic analysis provides a lot of really good data. You're actually watching the malware run, and if it doesn't short circuit itself, then it will go all the way through to reaching out to the C2 server, which is ideally what you want to have. Usually that's not the case. So one thing that we found out real fast with dynamic analysis in our guest machine, the one that was injected with the cuckoo agent, we had to do a lot of patching for that machine to make it look like every other box. So there's a great utility out there called PA-Fish to analyze your guest machine and keep it from being detected as much as possible by the malware sample. So this is really a cat and mouse game. I'm trying not to be detected as I'm running a malware sample in my sandbox, and it's trying to detect me, and we're fighting back and forth. That's why I mentioned back in the static analysis part, it would be great if we were able to patch the malware, like a bad piece of software, and get it to work all the way through. Other interesting parts about this, now I have a cuckoo cluster that I administer, and each box runs 8 samples at a time, and I didn't isolate every VM instance. So one thing that I found is that you can actually watch viruses attack other viruses across the VM network space. So it's kind of fascinating. Anyway. So the last part, once you get all these features generated and stored in some system that can handle it, now's the real fun part, is intelligence. Generating machine learning, or actually coming up with a machine learning algorithm that's able to generate data or models that fit your data. So machine learning is thrown around, it's used as a buzzword in a lot of sales, but in particular, there's 2 things that we want to do with machine learning. We want to do categorization, and we want to do prediction. So we get a lot of unknown binaries from the organic sources. We need to figure out whether they're good or bad. We see those coming across the network, we see file hashes. We need to know, or we need to come up with a way to say, this is probably good, probably bad, for all the unknown sources. This is the problem space that every AV vendor is in. The other thing is we need to categorize malware, because we may see hundreds of thousands of samples a day, but only a small fraction of those are new samples. Everything else is really just repackaged, rehashed. There was talking to a guy at lunch today about the Kaspersky thing that came out, where y'all read about the Kaspersky case or news article. 2 years ago, Microsoft accused Kaspersky of generating their own malware samples, not infecting their clients with them, but generating new malware samples and uploading that to VirusTotal to skew the results from VirusTotal about which AV vendor was more accurate. Effectively, what they were doing was back in the static analysis phase that I was showing them earlier. They would take a file, they would change one bit, which would change the entire hash of the file, they would throw it right back into VirusTotal. And they would say, we mark it as bad. Which, of course they did. They knew it. So, machine learning, two main goals, categorization and prediction. The categorization, we generally don't know what we're looking for. We just want to, we don't know how many categories of malware there are. So what we're doing is we're fingerprinting the files based on entropy is what we use. We use Shannon, just a basic Shannon entropy calculation on the file as a whole and then the different sections. As you know, if it's a file like a PE file, then we can break up the sections in the header and we can fingerprint each one of those. That gives us a good vector of how similar these files are together. So, categorization is unsupervised learning. So, we let the algorithm just generate how many clusters it finds. And then that's what we use to determine whether we have what we used to call an emerging hash, or something that's coming up that we haven't seen, it doesn't fit in any one of the clusters that we have so far. It's something new. So that's how we generate that. The second type, last type of machine learning that we found so far, or that we've used so far, is prediction. Now, prediction, like I said, is good or bad. Prediction is really aided if you have some authoritative source to tell you that this sample or this data is bad. So, going back to the synthetic speeds, most of those vendors will give you the files and say, we mark them as bad. Or if you throw it up to VirusTotal, or there's a few other places that you can look for a RESTful result. So you've got bad files. And then one thing that we do in our dynamic analysis is we inject it with known benign files. We actually take the Alexa top 2000, run it through Internet Explorer. So that generates a lot of noise and a lot of traffic. All of that traffic is marked as benign. So you've got, out of that, you've got good, and known bad. And those are the supervised, that's the supervisory set of data that we run through our classifier. And that gives us a good model to run over the rest of our unknown files and say this one's probably bad, probably good. Now, the cool thing about the pipeline that we've set up, and if you're, the whole point of this talk too is that if you were analyzing malware or seeing files across your system, you could set up the same sort of pipeline and come up with a way to analyze, or come up with a way to prioritize some files over others in order to analyze them. We use our this is where the predictive analytics also comes in. If it's probably good, then we increase the score and we prioritize those to go through the dynamic analysis and static analysis. Lower the score, lower priority. The reason is every step of the way, the feature generation, surface, static, and dynamic, they get progressively slower, like orders of magnitude. So we actually use our own pipeline and feed back into itself the prediction sets. So theoretically, we're getting smarter. So we still have to work with some of the papers around that. But anyway, that's what I've been working on. It's wonderful. There's actually a ton of technologies involved with it. I'll mention a few of the frameworks, and some of the systems behind it. So if you're interested in the nuts and bolts of the technology, feel free to ask. I'll go ahead and tell you that there's 3 clusters that we use for the pipeline. There's the control cluster, the Cuckoo cluster for running dynamic analysis, and the Malware cluster, which is our Hadoop system for machine learning. So all the tools that you have to use for cloud maintenance or cloud automation, all that stuff, we have to use that here to get everything together. The only one of the big differences is, especially with our Cuckoo cluster, when we pull samples off, we assume that those servers are tainted in some way. So we have to come up with other automation to wipe them all out, install Cuckoo automatically, and bring it all back up. So with that, any questions?
How often do you have to recalibrate when you're running through? Like, does it go through smoothly one time and then?
It's pretty lumpy. The question is, how often do we have to recalibrate our dynamic analysis?
Right.
And the answer there is the yield from dynamic analysis it varies greatly. What we do is every 4 hours I'll wipe out all the boxes.
Oh, okay.
So I'll recycle them every 4 hours. I've played with that every day. Week was way too long. An hour was way too short to get a good yield out of it. Part of it is a sample will run, and we give it a good 5 minutes for it to run. One thing we also notice with samples is that many of them are time-based. So we have to effectively time warp the system. As time goes on, it skips forward in time at an exponential rate. So by the end of the run, it should be like 5 years in the future. Hopefully it'll have decided to run then. But the time-based execution is also better with the static analysis patching the malware, because that's another check.
Oh, yeah, I was going to say, yeah.
So, that whole dynamic analysis is a whole.
So it's still trial and error. You don't.
Yeah.
Yeah.
Yeah, it is, because like I said, every step of the way it's fighting you. The only step where it's not fighting you is after you generated the features, which that's the part I like working.
Oh, yeah.
Because it's finally clean there. Clean data. So.
Are you guys using some kind of taxonomy like sticks or something like that for once you pull out IPs or interesting different things from the samples?
Yeah, great question. Whether or not we use taxonomy like sticks, we actually use sticks and OpenIOC, generating those from both static analysis and dynamic analysis. So we don't have a reconciliation process just yet for the 2 different types of files that we generate. But, oh, and manual analysis. If one of our analysts comes along and generates their own sticks file, that actually helps them out because it gives them a head start on sticks generation.
Do you all store those in a database, or do you just keep them as individual flat files per sample?
It's kind of a thorny subject, but yeah, we're storing these flat files right now.
Right.
And lobbying to turn that into a graph storage.
Yep.
Which is something that I would heavily recommend. Also with this, pick a graph storage system at the very beginning. Probably BT205 or Terabytes, something like that. Depending on how large your fees are going to be.
So when you find repetitive, just for instance, malware that's out there that you know is repetitive, now you got that signature for that particular one, and then it's in that's what you push out customer-wise, or? Okay.
Yeah, we don't know if we sell a feed of malware intelligence right now by itself. I know it's bundled in with our other products, but we actually forgot to mention this on the organic sources. once the server is infected, that server is probably going to have every URL you try is going to be malicious. That's one thing I've seen. So the crawler itself has to be smart enough to know, I'm getting bogged down with the server, I need to not. It's returned the same file 50,000 times.
So in essence, you got to create a normalization table for it too. Yeah.
Normalization, or that's where the graph databases come in very handy.
Just a quick question. You have, you said you're running 8 samples at a time at 5 minutes apiece. How many clusters do you have running?
8 right now. And that's, I don't think we're scaling it up right now, but there's talk of that. Personally, even though dynamic analysis is really sexy, I like static analysis because I think it scales a lot better. It's something that you can actually, you can run on hardware systems like GPUs to actually boost your processing power. Dynamic analysis looks nice, but I don't think the hypervisors will scale.
So when you look at samples via entropy per section of the PE file, you're saying that that's a good way for you to cluster, just because if all the sample A and B have the same entropy per section header, is that how you do it?
If they have the similar entropy, yeah. And it's actually more, so the machine learning part is not just one-to-one on entropy, it's entropy in similar groupings of sections.
Right.
So one of the first routes I took with this was trying to set up a neural network for that. And a neural network, real fast, is just, you have your inputs and then you have your outputs. In the middle you have hidden layers. Those hidden layers are the way that they explain it is synapses in the brain. So these two inputs, when seen together, usually give a strong correlation to this output. This is a real simple way to put it. But that's where the entropy, groupings of entropy come into play. So that's why, to give you an idea of the features, I spent a lot of time on that because an average, or a decent set of features would be somewhere around 50 to 100,000. And if you look at that from a regular perspective, it would be like 50 to 100,000 columns in the database, which is obviously not going to work well for something like MySQL or any other relational database. That's why specialized key value storages exist, like HBase. Don't think Cassandra is really geared towards it, but see those really wide things. But that's why we generate so many features so that we can come up with those hidden vectors. But going back to your question, entropy I've found is the best one for clustering. There's also things like language. That's why you're pulling strings out and then figuring out what's the predominant language, or a mixture of languages. So, I think it was the Sony hack. It came through Korea. So malware is actually a conglomeration of several different pieces of code. So they'll get a packer from over here, and they'll get a domain generator from over here, and a few other pieces. That's why I say that it's helpful to go through static analysis to go ahead and just say, hey, this is an off-the-shelf DGA. So don't worry about going into that. We've already seen that piece. That's what saves our analysts time. It's really cool stuff. I love working on magnets and malware. It's also maddening too. The whole title of the talk came from, well, first of all, the requirements were really vague in the beginning. Second is, every step of the way is just a whole area by itself. Static analysis is a whole field. Setting up the dynamic analysis is just a challenge in itself, scripting the Windows installations and all that stuff, and then trying to hide yourself from the malware that's running. Then just on top of all that, a cloud setup where you've got hundreds of thousands of samples coming in, and moving that through the process, and then spitting out useful data in the back end. All right.
So is there any trivia questions you could come up with quick to help us give away some goodies?
That's a great question. So, does anybody know the name of the product that the Norse map is attached to?
For a lockpick kit?
For a lockpick kit.
What was the question?
The name of the product that the map is attached to. Norse is. Nobody ever pays attention to the product. It's always the name.
I heard it's Norse. I think we're talking about Norse mythology.
That's
Well, we do use a lot of Norse mythology internally. The name of the pipeline, code name is Gavchen.
Gavchen.
Yeah, Norse god of cheese and stuff.
That'd be Loki.
Not Loki. I'll have to go look it up. Gavchen.
They definitely would not have named it Loki, I'm pretty sure. Got another one? Put you on the spot, huh? So, okay, how about for a lockpick kit, firsthand, which year of BSides Augusta is this year? Okay, right here in the red. Third, correct. That's for a lockpick kit. There you go, from Southward or Southern, I'm not really sure how you pronounce it. So for Blue Team Handbook, Incident Response Edition, I just have to know, what are you knitting?
A shawl.
A shawl?
Yes.
Okay, while you're in here learning Blue Team stuff, I think you deserve a Blue Team Handbook. Just for knitting, and that's all. That's the first time I've ever, well, second, that's what you do in the tabletop, good.
Right.
So, pretty awesome. Try to put you on the spot. Okay, and our final thing, come up with one? Did you come up with one? No? Okay. All right, it's all good. It's all good. This is for a disk duplicator. Does anybody have a need for that? Okay. Are we like a real disk duplicator? I don't know, like how's
What are these things that you speak of?
Yeah. Yeah, like why do you need that anymore?
5.25 floppy.
It's like if you're working,
Duplicate them.
if you're working with antiquated technology for backwards.
It's a trap.
That's it.
So we're gonna have to go. I guess we'll just go easy. Standard TCP port for LDAPS. Go.
636.
I saw this here. Go ahead, Trent.
636. He can have it.
You guys can argue over it. Okay, thanks guys for coming out. Thanks, Wes. So there are still